A slow, measurable collapse is unfolding in one of the most closely monitored mountain systems on Earth, and yet its implications remain widely underestimated. How does a land known for precision, stability, and long-term planning find itself confronting a loss it can no longer prevent? How does an entire continent depend on frozen water that is no longer staying frozen? And what does it mean when a natural system that has operated reliably for 10,000 years begins to fail within the span of a single human lifetime? Switzerland's remaining glaciers are no longer simply retreating. They're entering a phase of rapid and irreversible decline. Among them, the Rhone Glacier stands as one of the most visible indicators of this shift. Once extending deep into the valley floor, it has withdrawn dramatically, exposing bare rock where ice had persisted for millennia. Measurements taken over decades reveal not a steady, gradual melt, but an acceleration that has intensified in recent years. The pace is no longer aligned with historical variability. It reflects a system that has crossed a threshold. For thousands of years, glaciers in the Alps functioned as highly reliable reservoirs. Snowfall accumulated during winter months, compacted into dense ice, and remained largely intact through summer. This process ensured a delayed and regulated release of water, feeding rivers long after seasonal snow had melted elsewhere. The Rhine and the Rhone, two of Europe's most significant waterways, are directly sustained by this mechanism. Their flow patterns, historically predictable, have underpinned agriculture, transportation, drinking water supply, and electricity generation across multiple countries. The scale of dependence is substantial. Tens of millions of people rely, directly or indirectly, on water originating from alpine glaciers. Hydroelectric facilities convert meltwater into energy, accounting for a significant portion of Switzerland's electricity production. Industrial sectors in downstream nations depend on consistent river levels for cooling systems and logistics. Agricultural regions rely on stable irrigation during increasingly dry summers. These interconnected systems were built on the assumption that glaciers would continue to perform their function indefinitely. That assumption is no longer valid. Recent observations have shown that glacier mass loss in Switzerland has reached levels unprecedented in modern records. In a span of just 2 years in the early 2020s, approximately 1/10 of the country's total glacier volume disappeared. This loss matched the cumulative reduction recorded over several decades in the late 20th century. The comparison illustrates a dramatic shift in pace. What once unfolded over 30 years is now occurring within a fraction of that time. Winter conditions have also changed in ways that compound the problem. Snowfall, which replenishes glaciers, has become increasingly inconsistent. In one recent winter season, snow accumulation dropped to roughly 1/3 of its long-term average. This deficit meant that glaciers entered the summer months with significantly reduced protective cover. Without sufficient snow to reflect sunlight and insulate the underlying ice, melting intensified. Warmer summer temperatures further accelerated the process, creating conditions in which glaciers lost mass at rates far exceeding historical norms. The consequences of this imbalance are not confined to visible retreat. Beneath the surface, structural changes are taking place within the ice itself. Glaciers are thinning, developing internal fractures, and losing the density that once allowed them to persist through warmer periods. In many cases, their lower sections, known as tongues, have become unstable. Access routes that once allowed close observation have collapsed as the ice beneath them weakened and disappeared. Efforts to slow the melt have been implemented in specific locations, most notably through the use of reflective coverings. Large sheets of synthetic material have been placed over sections of glacier ice during the summer months to reduce heat absorption. These coverings have demonstrated localized effectiveness, preserving several dozen meters of ice thickness, or roughly over 100 feet in protected areas, and reducing melt rates significantly. However, their impact remains limited in scope. Covering entire glaciers is not feasible, and even in protected zones, the broader environmental conditions driving the melt remain unchanged. The limitations of such measures highlight a deeper issue. The processes governing glacier behavior operate on timescales and physical principles that are not easily altered through short-term interventions. Once a glacier begins to lose mass consistently, it enters a feedback loop. Reduced surface area leads to increased exposure of darker underlying material, which absorbs more heat. Thinner ice melts more quickly, further reducing its ability to persist. These dynamics reinforce each other, making reversal increasingly unlikely. Even in a scenario where global emissions were reduced immediately and dramatically, the outcome for many glaciers would not change in the near term. This is due to what researchers describe as committed loss. Glaciers respond to climatic conditions with a delay. The warming that has already occurred continues to influence their behavior for years or even decades. As a result, current observations reflect not only present conditions, but also past climate trends. The decline visible today was set in motion long before it became apparent. This delayed response creates a disconnect between cause and effect. Decisions made decades ago are only now manifesting as accelerated ice loss. Likewise, actions taken today will influence glacier behavior well into the middle of the century. This lag complicates efforts to address the issue, as the visible outcomes are not immediately tied to recent changes in policy or emissions. The Rhone Glacier provides a clear example of this progression. Historical records, including photographs from the 19th century, show a vastly different landscape. The glacier once extended far beyond its current position, filling the valley with thick, continuous ice. Over time, it has retreated by more than 2 kilometers, equivalent to over 1 mile. In recent decades, the rate of retreat has increased, with significant portions of the glacier disappearing within a single generation. The thinning of the glacier has also been substantial. Measurements indicate a reduction in ice thickness exceeding 100 meters or approximately 328 feet in certain areas. This loss represents not just a change in surface position, but a fundamental reduction in the glacier's volume and structural integrity. As the ice diminishes, the processes that sustain it weaken, accelerating its decline. Across the Alps, similar patterns are emerging. Larger glaciers, which once appeared more resilient due to their size, are also experiencing significant losses. Some have already lost a substantial percentage of their volume over the past few decades. Smaller glaciers, lacking the mass to withstand prolonged warming, have disappeared entirely. The overall number of glaciers in the region is decreasing, and those that remain are shrinking at an accelerating rate. Projections, based on current trends, indicate that a significant portion of alpine glacier ice will be gone within the next few decades. If global temperatures continue to rise toward levels already approached in recent years, the majority of these glaciers could vanish before the end of the century. The timeline for the most rapid losses is expected to occur within the next 1 to 2 decades, a period during which the rate of disappearance may reach its peak. The implications of this shift extend far beyond the mountains themselves. Rivers fed by glacier melt are already exhibiting changes in flow patterns. In some cases, increased melting has temporarily boosted water levels during spring and early summer. However, this is followed by reduced flow later in the season when water demand is highest. The long-term trend points toward decreased overall availability, particularly during periods of drought. Hydroelectric power generation, which depends on consistent water supply, has begun to experience variability. Facilities designed for stable input are encountering fluctuations that complicate energy production. During dry years, reduced water levels can lead to decreased output, affecting both local supply and broader energy markets. These changes introduce new uncertainties into systems that were built on the expectation of reliability. Agriculture is also affected. Irrigation systems that rely on glacier-fed rivers are facing challenges as water availability becomes less predictable. Farmers must adapt to conditions in which water supply may be abundant at one time and insufficient at another. This variability complicates planning and increases the risk of crop loss, particularly in regions already prone to dry conditions. Transportation networks that depend on navigable rivers are encountering disruptions as well. Lower water levels can restrict the movement of goods, increasing costs and affecting supply chains. These impacts are not isolated, they ripple outward, influencing economic activity across multiple sectors and regions. Despite the growing evidence, large-scale adaptation measures have not kept pace with the rate of change. Infrastructure designed for a stable climate is being tested under conditions it was not built to handle. Adjustments are being made, but often incrementally and in response to immediate pressures rather than long-term projections. This reactive approach leaves systems vulnerable to further disruptions as conditions continue to evolve. The broader European context reflects similar trends. Glaciers in other mountain ranges, including the Pyrenees and the Carpathians, are also declining. The pattern is consistent: reduced snowfall, higher temperatures, and accelerated melting. While the Alps remain one of the most studied regions, the processes observed there are not unique. They are part of a larger shift affecting mountain environments across the continent. Public awareness of these changes has increased, but attention often focuses on visual indicators, such as retreating ice fronts and exposed rock. While these images convey the scale of change, they do not fully capture the systemic implications. Glaciers are not isolated features. They are integral components of complex networks that support human activity on a large scale. As the remaining ice continues to diminish, the effects become more pronounced. Seasonal patterns shift, resource availability fluctuates, and systems built on long-standing assumptions must adjust. The transformation is ongoing, measurable, and in many respects already advanced beyond the point of reversal within any near-term time frame. The pace of change is no longer theoretical or distant. It is already shaping how water moves through Europe, altering timing, availability, and reliability in ways that infrastructure was never designed to accommodate. As glaciers shrink further, the immediate effect is not an abrupt disappearance of water, but a distortion of its seasonal rhythm. During the earlier phases of accelerated melting, rivers can temporarily carry higher volumes, particularly in late spring and early summer. This creates a misleading impression of abundance, yet this surge is finite. It represents stored ice being released faster than it can be replenished. Once that stored reserve diminishes beyond a critical point, the pattern reverses. River discharge declines, especially during the hottest months when demand is at its peak. This transition is already being observed in multiple alpine-fed systems. The shift from consistent glacier-regulated flow to precipitation-dependent variability introduces a level of unpredictability that affects every sector tied to water. Hydropower systems are among the first to register these changes in measurable terms. Switzerland's energy network has long relied on predictable meltwater cycles to sustain electricity production. Reservoirs are filled through a combination of snowmelt and glacial runoff, allowing operators to regulate output throughout the year. As inflows become less reliable, the balance between supply and demand becomes harder to maintain. In years with reduced summer runoff, electricity generation declines, forcing greater reliance on imports or alternative energy sources. In contrast, periods of excessive melt constrain storage capacity, requiring rapid adjustments to prevent overflow or inefficiencies. This growing volatility challenges a system that was engineered around stability. The infrastructure itself remains functional, but the environmental conditions it depends on are shifting. Over time, maintaining consistent output may require substantial redesign, including expanded storage, altered release schedules, and integration with other energy systems that can compensate for fluctuations. Agriculture faces a parallel set of pressures. Irrigated farmland across parts of Switzerland, France, and northern Italy depends on water originating in the Alps. Traditionally, glacier-fed rivers provided a dependable supply during dry periods, buffering crops against seasonal drought. As that buffer weakens, farmers encounter increasing uncertainty. Water may be plentiful at one point in the growing season and insufficient at another. Crops that require steady irrigation become more difficult to manage, and yields can decline as a result. In some regions, reliance on groundwater has increased as a temporary solution. However, groundwater reserves are not an unlimited substitute. They recharge slowly and are themselves influenced by precipitation patterns that are becoming more erratic. Overuse can lead to long-term depletion, compounding the challenges already posed by glacier loss. The shift from a stable surface water system to a more fragile combination of sources introduces risks that extend beyond individual growing seasons. River transport, a less visible but economically significant component of the system, is also being affected. The Rhine, one of Europe's primary commercial waterways, has experienced periods of unusually low water levels in recent years. When river depth falls below certain thresholds, cargo vessels must reduce their loads or suspend operations altogether. This disrupts the movement of goods, increases transportation costs, and places additional strain on alternative logistics networks such as rail and road. These disruptions are not isolated incidents. They reflect a broader pattern linked to changing hydrological conditions. As glacier contributions to river flow diminish, the frequency and severity of low water events are expected to increase. This has implications not only for trade but also for industries that depend on river water for cooling and processing. Reduced availability can limit production capacity, affecting supply chains that extend far beyond the immediate region. The transformation of alpine landscapes is equally significant from a physical and geological perspective. As glaciers retreat, they expose terrain that has been covered for thousands of years. This newly uncovered ground is often unstable, composed of loose sediment and fractured rock. Without the stabilizing presence of ice, slopes become more susceptible to landslides and erosion. In some areas, entire sections of mountainsides have begun to shift, posing risks to infrastructure such as roads, railways, and settlements. Glacial lakes are also forming in increasing numbers as meltwater accumulates in depressions left behind by retreating ice. While these lakes can appear stable, they carry inherent risks. Natural barriers composed of loose debris can fail without warning, releasing large volumes of water downstream. Such events, known as outburst floods, can cause sudden and severe damage. Monitoring these lakes has become an essential component of managing the changing landscape, yet the number of potential sites continues to grow as retreat accelerates. Tourism, a major contributor to the Swiss economy, is undergoing its own adjustments. Glaciers have long been central to the country's identity, attracting visitors for their scale, accessibility, and visual impact. As ice recedes, some of these attractions are becoming less viable. Ice caves collapse, viewing platforms require relocation, and traditional routes for hiking and mountaineering are altered or closed. While new forms of tourism may emerge, the transition involves both economic and logistical challenges. The symbolic dimension of glacier loss is difficult to quantify but widely recognized. Glaciers have represented permanence, endurance, and natural continuity. Their visible decline alters not only the physical landscape, but also the cultural perception of the environment. What was once considered stable and enduring is now understood to be temporary and vulnerable. Looking ahead, projections indicate that the coming decade will be critical in determining the extent of remaining glacier coverage. The rate of loss is expected to peak within this period, driven by the combined effects of past warming and ongoing climatic trends. Smaller glaciers are likely to disappear entirely, while larger ones will continue to shrink at accelerated rates. By the late 2020s, some of the most studied glaciers may exist only in fragmented forms, no longer functioning as cohesive bodies of ice. The concept of a last glacier is not tied to a single location, but reflects a broader reality. The system as a whole is approaching a point where only remnants remain. These remnants will be significantly reduced in size and function, unable to sustain the roles that glaciers have historically played. Their presence will be more symbolic than practical, marking the final stage of a long process of decline. Adaptation efforts are beginning to take shape, though their scale varies. Water management strategies are being revised to account for increased variability, including the construction of additional reservoirs and the modification of existing ones. Agricultural practices are being adjusted, with shifts toward crops that require less water or can tolerate greater fluctuations. Energy systems are exploring diversification to reduce dependence on hydropower alone. However, these measures require time, investment, and coordination. The pace at which they are implemented will influence how effectively societies can adjust to the changing conditions. Delays increase the risk of disruptions, as systems designed for a previous climate continue to operate under new and less predictable circumstances. If you found this breakdown clear and informative, make sure to like, share, and subscribe for more in-depth reports like this. Tap that hype icon to help this video reach a wider audience and keep important information like this visible to more people.